Good morning. Can you guys hear me? Can just write in the chat just to confirm that you have sound on this webinar. I see something. Yes, thumbs up from Annette. I think we'll just give it one more minute and then we can start the webinar. Excited that we are quite a few people here with quite a broad and different background. So it's going to be interesting to have this webinar for you guys. For those of you that doesn't know me, my name is Daniel. I'm the CEO of ETN, the company that has commercialized the EME technology. So we have developed the first instrument called ETN 12. This is an instrument that can do 12 extractions at a time. And our goal is now to launch the 96 well system in March of 2026. And together with me, we have Stig Pedersen Bjerregaard. He is the inventor of EME, and he will today discuss the newest applications and research of EME. I think we can actually start right away, Stig, if you want to take over.
Yeah. So I hope you can see my screen. It's okay?
Yeah, you can see it.
Yeah. So good morning, ladies and gentlemen. Welcome to this webinar on electromembrane extraction. My name is Stig Pedersen Bjerregaard, and I'm at the University of Norway and also the University of Copenhagen in Denmark. So in this webinar, I will just briefly go through theory, a little bit about equipment, procedure, a method example, and discuss a little bit selectivity. I will try to be short here because I guess that most of you already know the basics of EME. Then I picked out a few papers published recently on the development of EME to give you an idea of what's going on in the forefront of research related to EME. And then at the end, we should have questions and discussions. So EME, or electromembrane extraction, is a microextraction technique where we extract analytes of interest with charge, either plus or minus charge, from sample solution, which is typically aqueous, through a thin layer of organic solvent immobilized in a porous membrane. We term this the liquid membrane, it's organic phase, and then further on into acceptor solution, which is an aqueous buffer solution. And the driving force for the mass transfer is an electrical field which is sustained across the liquid membrane. And then after extraction, we can pick the acceptor and analyze directly by LCMS or related techniques, because the acceptor solution is purely aqueous. So the first paper on EME was published in 2006. Since that time, close to 600 articles have been published on EME in literature. Many authors and many countries and many research groups have been part of this development. And very interestingly, last year, commercial equipment was released for EME. So with the commercial equipment is based on the use of vials of conducting polymer. So you can see the vials here. So we use one vial for the sample solution and one vial for acceptor. And then there is a membrane. Here's a dry filter membrane, which is located into this membrane union, and this membrane union can combine the two vials. So we get a system, as you can see here. We have sample solution, we have liquid membrane, we have acceptor solution, and the electrical field is coupled directly to the containers because they are made of conducting polymer. Here you can see the apparatus with the power supply and the shaking system, and the plate here where you can load 12 samples for simultaneous extraction. And this, of course, is controlled from computer. So when we do EME with this equipment, we first fill samples into the sample vials. We then fill acceptor solutions into the acceptor vials. We attach the membrane union and the dry filter, as you can see here in step 3. In step 4, we pipette the organic solvent onto the dry filter. In a couple of seconds, the organic phase is penetrating the porous membrane, and it is held there by capillary forces. So then we have loaded the liquid membrane. Then we combine acceptor and sample vials into this extraction unit. And we put the extraction units into the 12-position holder of the extraction apparatus. And we have a lid here that we close. And when we close the lid, you can see the contact electrodes here. They will come in contact with the surface of the conducting vials, and by such the electrical field is coupled in the system. We then turn on agitation and voltage. You can see here now the system is closed and ready for extraction. Extraction takes place by applying the voltage delivered by this cable here, and also we have shaking in the box. And after extraction, we just pick out the acceptor vials and put them directly into the LCMS auto sample. So in EME, the mass transfer or the extraction process involves electro-assisted partitioning of the analytes from aqueous sample into organic liquid membrane. And then we have an electrokinetic migration of the analytes across the membrane, but also to some extent diffusion. And then when it comes to the borderline to the acceptor solution, we have another electro-assisted phase transfer or electro-assisted partitioning into the aqueous acceptor solution. So it means that because we have such system, we get very nice cleanup. So if we have a system tuned for basic analyzed like this one, then we have the minus electrode in acceptor, we have the positive electrode in the sample, and we have a relatively non-polar liquid membrane. This substance here, which is the analyte, can pass the membrane and get extracted. But if we have more polar bases, they cannot enter the membrane. Salts cannot enter the membrane because the membrane is too hydrophobic. And neutrals and acids, they will not move in this direction in the electrical field. So the system will discriminate most of the other components in the sample, and therefore we get a relatively or very clean extracts. Here is one example of a method. So now we are looking into a method for extraction of fluvoxamine. This is an antidepressant drug, and we are to extract this drug substance from human plasma samples. So we pipette 125 microliter plasma into the sample vial. We add a similar volume of dilute formic acid to acidify the sample, because now we are to extract a basic substance, so we need to get this group here protonated in order for the substance to migrate in the electrical field. And when we dilute with formic acid, we adjust the pH in the plasma to 2.5. The liquid membrane is nitrophenyloctyl ether. You can see the structure over here. We often call, or we abbreviate this solvent NPUE. It's the most popular liquid membrane in EME. And 7 microliters is used to fill up the the porous volume of the filter that holds or support the liquid membrane. And then the acceptor solution is 250 microliter, 100 millimolar formic acid. Again, acidic conditions here to make sure that the analytes are migrating towards the right in the figure in the electrical field. We then apply the electrical field. We put the minus electrode in contact with the acceptor because we are to extract positively charged compounds from sample and into acceptor. We also shake the system because the transport of analyte from bulk sample and to the membrane is mainly by convection, so strong agitation is important. And when we apply the voltage, the current that flows in the system is approximately 1 microamp per sample. We measure this current continuously because it gives us information about the flux of ions across the membrane. And also, very importantly, it gives us a very good support for the stability of the system. So if something happens to the liquid membrane, we can immediately see it from the current profile. We extract for 15 minutes, and then we analyze directly the acceptor by LC-MS. And as you can see here, fluvoxamine and some related basic pharmaceuticals, log P values from 2.8 to close to 5. They are all in this system extracted with very high recovery, close to 100%. And as you can see here, the linearity, repeatability, accuracy, and matrix effects are within the recommendations given by medicinal guidelines for analysis of pharmaceuticals in plasma. So we can rely on the data when we combine EME with LC-MS. Just to finish off this initial theory part, a few words about selectivity, because in EME, if we use the system I just showed you with NPV as a liquid membrane, we extract very efficiently basic substances with log P3. So they go very fast into the membrane, but they also go fast out of the membrane again and are extracted with high recovery in the accepted solution. If we look into more polar bases, like a substance with log P 1.0, this very polar substance cannot penetrate the membrane, so it remains in the sample. It is not extracted. And also, if we look at what happens to a very hydrophobic base, then this substance here will be extracted very fast into the liquid membrane, but it will remain there due to hydrophobicity and will be not extracted into the acceptor solution. So if we plot the recovery of these three compounds as function of their log P values, we get a diagram like this. Only the log P3 substance is extracted. Well, this is a theoretical figure, but if we look into real data from our lab, here we have measured a recovery for 90 different pharmaceuticals. They are all bases from log P -3 to log P +8. We use the NPV solvent as the membrane and 50 volts as the extraction potential. And you can see that from log P2 to about 6, and more or less all these substances are extracted with very high efficiency. At lower log P, the substances are too polar to enter the membrane, and above log P6, they are so hydrophobic that they remain in the liquid membrane. So, and therefore, because we have transport in and out of liquid membranes, EME systems typically extract in windows like this. With NPV, it's from 2 to 6, but we can change the solvent and either shift the window to more polar substances or to more hydrophobic substances, but we can also tune the size of the window based on the electrical field. Recently, we have published a set of generic methods because the chemistry in our EME systems are very different from what analytical chemists are used to. So therefore, we have developed a set of generic methods that people can use as a starting point for their method development. I will not go further into this. We can probably come back to that in a later webinar. Then I will shift a little bit and look into a couple of scientific publications to give you an idea of what is going on in the research related to development of EME. And first, to mention, there are about 600 papers in the scientific literature on EME. This year, there are currently 35, but it will probably end up with about 50 papers this year. And I would like to show you a few examples of how people develop applications, how they develop generic methods, how they do EME with aqueous gels rather than organic liquid membrane, and also how this EME principle is transferred into microfluidic devices and paper analytical devices. So this is just to give you a flavor of what is going on in the forefront of EME. So the first application I would like to draw your attention to is work done in Czech Republic, but in some collaboration with us here in Oslo. So we try to collaborate as much as we can with different groups to assist them in their method development because we have long experience with that. So in this case here, the sample is whole blood, and the analytes are basic substances or pharmaceuticals in the log P range from 2 to 6, and with molecular size less than about 400 Daltons. And the whole blood samples in this case are picked up with the volumetric absorptive microsampling device, which is a small tip of a polymeric substrate, it's porous. So when you dip this into a blood droplet, it takes up a well-defined volume of whole blood. And then so you sample the sample with this VAMS device, and then you detach the tip with the blood sample. And in our case, we put that directly into a sample vial for EME, and we added formic acid with some methanol as the desorption liquid. So in this chamber here, the analytes were released from the blood matrix into this formic acid methanol solution. And this, of course, is a very dirty solution because more or less everything from the blood sample will be dissolved in this liquid. So therefore, we did EME to clean up very efficiently this fluid. So we used the NPV membrane because, as we just discussed, it has a extraction window from log P 2 to 6. So it's perfect for this application, and extracted into 100 millimolar formic acid in the acceptor solution. And because we are dealing with basic substances, we need the acidic conditions to make them protonated, and we put the minus electrode at the acceptor for the cations to move across the system. And then the acceptor can just be analyzed directly by LC-MS. So hopefully the VAMS technology has been quite popular and successful, and we hope by this application here that people will also take advantage of this coupling to the EME technique to really get a clean extract from the blood sample. Here is another application. This is extraction of morphine, and morphine is both a base and an acid, so it's a sweeter ionic compound, and it has a log p-value of 0.7, so it's a relatively polar substance. And in this case, the authors, these are Iranian scientists, they did the extraction from urine. You can see the device here. So this is a home-built device where the yellow color indicates the urine sample. Then there's a small insert here in the sample with a green color in the bottom, and this is the membrane, and then the blue color is the acceptor solution. And you can see that the minus electrode is inserted into the acceptor. So it means that in this case here, they are extracting morphine as a base under acidic conditions. But the most important part in this system is the membrane, because this is not a organic solvent, but it's a aqueous gel. So they use a alginate polyacrylic acid agarose mix gel, as you can see the structure over here. So it means that this system is a totally aqueous system. The sample is aqueous, the membrane is aqueous, and also the acceptor solution is aqueous. In contrast to the traditional EME system, where as we saw in previous example, where the sample is aqueous, the membrane is organic, and the acceptor is aqueous. So the advantage of this gel EME system is that larger biomolecules, they can pass through the membrane and into acceptor, and also very polar substances can move across the membrane in the system. So the gel systems, they are interesting for very polar and large molecules. So that is the advantage of gel EME. On the other hand, there are two challenges with this system. Because it's purely aqueous, and when you apply the voltage, you get very high current in the system because you have high conductivity in all three phases. So you easily get electrolysis and joule heating of the system. And also water can move in the system, so the volumes of acceptor and sample can change as function of extraction time. So there are some interesting aspects with the gel system, but there are also some problems or challenges. The third application I would like to draw your attention to is this paper here by Chinese scientists, published in Forensic Toxicology. You can see that they have not used the ETN device, but they have used a home-built system in a small tube. Here is the electrode for the sample solution, which is down here. And here is the electrode for acceptor solution, which is in here. And then the membrane is somewhere down here. They were extracting cat. So they were extracting from plant and this is forensic toxicology. So the sample was actually fluid from eyes from dead people, and they especially looked into these norephedrine, and catinone substances. They are bases with log P around 1. So they were extracted in this system. And of course, they studied different operational parameters and optimized this system for those substances. Here you can see the optimization of the system for with respect to the organic phase, the liquid membrane solvent. You can see that the 3 compounds, when they were extracted with NPV, recoveries were low. And this is because these substances here, their log P value is outside the extraction window of NPV. And then you can see that recovery varies significantly with the organic membrane. So the composition of the liquid membrane is a key parameter in EME and has to be optimized. In this case here, they found the best membrane was the membrane number 7, which is ethyl nitro benzene and undecanol in combination. So this is quite typical for a lot of EME research, that people have put quite a lot of efforts to find the best liquid composition. And I will come a little bit back to that in my next, or a little bit later. Here is extraction of ochratoxin A from plant material. You can see the structure of the substance here. So it has both acid and base properties. It's relatively hydrophobic with a log P more than 4.5. Again, this is also people from China. They used a home built system, but it's similar in performance to the ETN device. And you can see here that they studied the different operational parameters. So again, they tested different organic solvents as liquid membrane. We can see here that NPV is not a good membrane for acids, and we know that, whereas the ketones and especially the alcohols are much better membranes for acidic substances. So the best membrane liquid was actually 1-octanol. They also investigated extraction recovery as function of voltage, and you can see that even with 2 volts, a very low voltage, they were more than 70% recovery. And when they increased up to 10 volts, they reached 100% recovery in the system. And this is typically that recoveries and efficiency increases with voltage up to a certain level. And if you go higher in voltage, then you might have a drop in performance because you get excessive current in the system. Also, they optimize time, and again, extraction recovery is increasing with time up to a certain level where the system comes to equilibrium, in this case after 20 minutes. And also here, if you continue the extraction, you might lose a little bit recovery because pH is changing in the system if you do very long extraction. And they finally optimized the pH in the acceptor solution, and as expected, the acid gets more and more ionized as you increase pH, and therefore it also extracts more efficiently. So therefore we see an increase in extraction recovery when increasing pH in the acceptor. Just to mention, because people, we think that if people always had to optimize liquid membranes and the other operational parameters, and in every case it's less EME is not that attractive. So we think that it's important that there are some generic methods that people can use more or less directly and take advantage of. And here is one example that we published, generic extraction conditions for acids with low or moderate hydrophilicity. So in this paper, we were able to extract acidic compounds very efficiently down to log P 0 or even log P -1, published recently in Analytical and Bioanalytical Chemistry. We are at the end, but I will just mention for you that we also see in literature now many efforts to integrate EME onto microfluidic or paper-based devices. And here is one example from colleagues in China, where they have made a system where they use a micro paper analytical device where they integrate solid phase extraction and electron membrane extraction to isolate nitrate from fat containing food and combine it with detection with a smartphone. So there are many examples like this where EME is integrated into microfluidic systems. And also there's quite a lot of work going on with this gel electro membrane extraction where there is no organic liquid membrane but an aqueous gel. I think we discussed that a little bit in the previous example, so I think I will finish here. Yeah, that was the end of the presentation or the lecture. So
thank you, Stig. Do we have any questions here from the audience? Feel free to use the chat function or Q&A, and I can also see if I can unmute you guys if you want. Meanwhile, Stig, could you elaborate a bit more about what you think will be the focus for or the possibilities for EME in the next 1 to 3 years, and what we can expect to see in the development of EME as a technology and the possibilities there?
Yeah, I'm thinking that as you saw here, all the papers in literature, most of them are with home built equipment. So I think this device from ETN is very important because people can buy it and use it, and it makes it much easier for other laboratories to repeat experiments. So I think this is very important. And then my thinking is that EME is a fundamental separation principle. So it's electrophoresis across an oil membrane. And I think this principle can have many applications in the future. So I think the next 2 or 3 years, I expect that people will buy more and more equipment and do more and more experiments and expand this principle in a lot of different directions. And in some cases, the EME methods that people will develop will be similar in performance to those already used by routine laboratories, but for other applications, they will see a real difference and when implementing EME. And especially the green chemistry aspects of EME is very interesting. I think many younger people, they will really focus on that.
Do we have any questions? We still have a couple of minutes if people feel that they have something they wonder about or want to discuss. Otherwise, of course, feel free to send us an email. I will send the recording of this webinar to all of the participants right after or later today. And if there are any questions for me or to Stig, yeah, feel free to send it on email also, and we will do our best to help you with the questions you have. Great. I think it was loud and clear. Then thank you so much, Stig, and talk to you soon.
Yeah, bye to all, and thanks for listening.
Yeah, and sorry for Jesper that had to leave because of a fire alarm on the site, but I think hopefully everything's fine there also.
Oh.
Great. Have a nice day.
Bye.